Hello everyone, welcome to our video. We're Group 9 here to talk about closed system, reversible process, and enthalpy. Our group consists of 3 members, starting with me, Areej, who will introduce the topic of closed system, Kesavan will talk about enthalpy, and Zhi San will elaborate on reversible processes. Let's start with the topic of closed systems. In 1824, Sadi Carnot described a thermodynamic system as the working substance of any heat engine under study. Nowadays, system is whatever we want to study. The region outside the system is called the surroundings. The thing that separates the system from its surroundings is called the boundary. It can either be fixed or movable. A closed system is defined when a particular quantity of matter is under study. It consists of a fixed amount of mass, meaning no mass can leave or enter a closed system. However, energy in the form of heat or work can cross the boundary. An example is a gas and piston cylinder assembly when the valves are closed. Another very good example of a closed system is Earth. We know that mass is conserved and energy can flow in and out of the system, which fits the definition of a closed system. Mathematically, a closed system can be expressed in this equation where each elemental atom is conserved.
Now let's move on to reversible process. Historically, the term Tesla principle was used to describe certain reversible process invented by Nikola Tesla. The principle states that some systems could be reversed and operated in a complementary manner. The definition of reversible process is a process in which the system and surrounding can be returned to its original conditions from final state without producing any changes in thermodynamic properties of universe if the process is reversed. Conditions for reversible process to occur are: the process should occur infinitely slowly because of infinitesimal gradient. All of the initial and final state of the system should be in equilibrium with each other, and there should not have any loss of energy due to conduction or radiation during the cycle of operation. Example process that is reversible are isothermal, isobaric, isochoric, and adiabatic process. Some examples of reversible process in our daily life are frictionless motion of solids, extension of springs, slow adiabatic compression or expansion of gases, and slow isothermal compression or expansion of gases.
So, I'm going to explain about enthalpy in a closed and reversible system. Enthalpy uses the root of the Greek word thalpos, which means warmth or heat. The term expresses the amount of heat gained in a process at constant pressure, but not in general cases where the pressure changes time to time. To clarify this, Josiah Willard Gibbs phrased enthalpy as heat function for constant pressure. We can define enthalpy as the sum of internal energy and product of pressure and volume. Thus, H equivalent to U plus PV. One of the important properties of enthalpy is it is a state function, which means enthalpy of a system only depends on the current thermodynamic state of a system, not the path which the system took to reach the current state. This is an example where we can observe enthalpy change phenomena where an ice starts to melt. Delta H equal to delta U plus P delta V is the formula for enthalpy calculation. By substituting delta U equivalent to Q plus W and W equivalent to negative P delta V, we can conclude a relation where change in enthalpy is equivalent to heat released or absorbed by a system.
Now, this is an example of a thermodynamic problem with all of the 3 topics that we discussed. From the statement, these are the following data. And this is our working solution using Microsoft Excel, which gives us these final answers. We also solved the problem using MATLAB, which gave us similar final answers. You can pause the video and look through the problem more in depth. And that concludes our video. Thank you so much for watching. Make sure you like, comment, and subscribe. We hope you learned something new today, and make sure to check out the references we used in the making of this video. Ciao!